Okay, I'm back. After a short break, after I did B3, it took like 1 hour to solve B3, which was the previous problem I solved. Now I'm looking at B4, and hopefully this one will take shorter. So let's read the problem. So we have a set of functions r squared to r that are twice continuously differentiable, and we define them on, well, actually it's not, it's more like 1 min t squared to r squared, yeah. And we have these two funny-looking equations, and we have, again, a funny-looking sort of expression here, which is a kind of sum over all squares in the domain of the function, like it's some kind of weird difference. So just looking at this setup, it reminds me very strongly of harmonic functions. So it feels like we ought to be able to do something using those. I admit that this is not my area of expertise, so it might not, I might not be able to solve it very efficiently. But let's think about it regardless. So one idea would be to try to define some alternative function which would be harmonic, but I'm really not sure how to go about doing that. Yeah, I'm not sure. I'm just differentiating the first equation with respect to x, so we're going to get xy, so y ln xy plus what's the derivative of this? It's going to be 1 over x, right? So it's going to be plus y, because this is, yeah. So it's this expression, and we can do the same for, obviously, because everything is symmetric. So that means we can get rid of the second order derivatives in these equations. We can say x so I'm trying to substitute fx plus y x ln xy plus x minus fy is equal to xy. Okay, so let's multiply this out. We're going to get 2xy ln xy plus 2xy, and then we're going to get some expression which is minus xfx plus yfy equals xy, right? Well, this is not very encouraging, because I think we end up proving like a... I'm just shaking what I did so far for mistakes. Xy, x ln xy times x. Well, that seems to check out to me. And then the problem is that we know what fx plus yfy is. We know that it's equal to xy ln xy, and then this equation doesn't seem to work in that case. So it's kind of a big mystery what's going on here. Yeah, because, I mean, we know that this is equal to this, right? So if you write plus 2xy minus xy ln xy, this is not equal to xy in general. So I must be making some kind of mistake somewhere, but I don't know. Hold on. I'll actually check if I actually transcribed this problem correctly. Yeah, I did. Yeah, I did transcribe it correctly. So that's a big mystery. I don't know what's going on here. It seems like I'm getting a contradiction. Okay, I didn't really expect this to go like this, but I'm totally mystified right now. Why what I'm showing seems to imply that there cannot be such a function f. And I'm not sure what I'm messing up. Right, because this is just straightforward. Oh. My god. I'm missing the partial derivatives, of course. Yeah, I'm missing the partial derivatives. So there should be, okay. There should be an f xy here and yff xy here. And then, because we're differentiating just like x, and then there should be an x fxy here. Okay. So then we multiply this by x and this by y. X squared f xx plus f x plus y xy f xy equals, and then multiply this by y, and we're going to get two things that are equal, right? Plus yfy plus xy fxy plus xy and xy. Yeah. So we get two things that are equal. And we happen to know the sum of each individual part here. So we know that these two sum to xy, these two terms. And then we know that these two sum to xy ln xy. And then there's this left over, which I suppose sums to 0, right? Because if these guys sum to xy, so this part, if you ignore the mixed partial, then the other two terms are here, are basically summing to the right-hand side. So we can deduce from this that if you just take sums but if you just sum them, then everything on the right-hand side is going to occur twice. So we're going to get basically 2xy fxy is equal to xy ln xy plus xy, or since x and y are always positive in our domain, we can divide through, we can get 2xy fxy equals ln xy plus 1. So this is what we get if we differentiate f with respect to x and then with respect to y. So f has to be some kind of integral of this expression. Like we can integrate with respect to y and then integrate with respect to x. So let's do that. Fxy equals ln xy x plus ln y plus 1. Integrating with respect to x, we're going to get 2f. Well, let's integrate with respect to y first. So integral of a constant is going to be y ln x plus y ln y minus y plus y, and then we'll add basically some constant function, which is only a function of x here. So this tells us the derivative with respect to x, and we can probably find something similar with respect to y. Basically, we integrate with respect to x first this time, and we're going to get x ln x minus x plus x ln y plus x plus, so c2y. I'm not sure if this helps us at all, but you know. We can obviously also subtract these two from each other. That might also help us, but I'm not sure. Because we don't really seem to know a lot about their differences. So this is kind of an interesting expression because it seems like it actually has to do with this mixed partial. Like, it seems like a discretized version of the mixed partial, if you see what I mean. In that case, it's plausible that it's going to be independent of all the other stuff that's going on. But I'll actually integrate this. So let's see what we can get here. So now we're introduced with the x, right? Minus xy. Actually, these cancel, right? Yeah, these are going to cancel, so you don't have to worry about those. And then we'll have basically, suppose we make this a derivative actually, and then c1x plus, since we're integrating with step x now, we must allow for c2y here. And let me see if it is sensible. Y seems like it's sensible. ln xy minus xy. So this is what I think we're getting. And then we have less plus c1x plus c2y, it's the thing here. So now let's look at this expression, right? F s plus. So the idea is that these c's are likely to cancel in this expression, and we're only going to be left with something to compute with here, right? So suppose we compute this now. So I'm going to first compute it for the constant part. For instance, this part is going to be equal to, since x is constant, this will cancel, and we're going to have c2s plus 1 minus c2s. And then f ss plus 1 minus fs plus 1. Same story. This will be c2s minus c2s plus 1 sums to 0. So what we show is that this part, when we take this square difference kind of thing, is going to vanish, and we're going to be left with only this part. And we have this factor 2 here, which I should remember. So basically, mf is independent of f and is equal to the minimum of this get evaluating at f equals xy ln xy minus xy over 2, sorry. So now we just need to evaluate this and minimize it, which is kind of frustrating. But let's write it out. Plus 1 squared ln minus s plus 1s, so plus ln s. So first I'm doing the xy ln xy term. And then we have a minus sorry, s plus 1. Well, actually this is symmetric, right? Yeah, so this function is symmetric, so, but those will not cancel. So yeah, well, since it's symmetric, we can just put a 2 here. And then we're going to have plus 2s squared ln s squared, right? ln s, yeah. So we're just going to end up with this. And then this is just for this part, and since we divide by 2, we're going to get rid of these factors of 2. And now we incorporate the term for xy. Xy is just going to be, I'm pretty sure xy is actually going to vanish here. But let's write that out anyway. So s plus 1 squared plus 2s plus 1 right, that's okay, that's true. And then minus s squared. And again, this is all going to be divided by half. So let's first check that this is actually 0. I'm pretty sure this is 0. So s plus 1 squared minus s squared is just 2s plus 1. and we're dividing by 2. Oh, but we're not subtracting. Sorry, we're adding these. Sorry. So this is 2s squared plus 2s plus 1 divided by 2 equals s squared plus s plus 1/2. And then we have this. So let's divide it into chunks. This part is going to be equal to s squared plus s minus this. So it's going to be just minus 1/2. Okay, so we've taken care of that. Now we have this annoying part. What's going on? Yeah, this notepad is behaving weirdly. So let's now compute this. Oh my god. This seems horrible. So, oh, okay. So this is going to be s plus 1, ln s plus 1, plus, sorry, minus s plus 1 copies of s. So s ln s. Okay. So, did we miss any? No, okay. So, s1 ln s plus 1 minus s ln s, and then we just have this constant 1 minus 1/2, which we can't, that doesn't affect the minimization at all, so we can just leave it. And now we're supposed to just minimize this. Now I think the problem becomes considerably easier because we just have to differentiate it. So, well, let's do it. The derivative of this is going to be ln s plus 1 plus 1, right? Because, yeah. And then minus ln s minus 1. So we're going to end up with ln s plus 1 minus ln s. Though if you set this equal to 0, then there's actually no solution to this, which is slightly disturbing. Makes me think if we missed out something earlier on. Yeah, I'm not sure. Because this does not equal, it's never equal to 0, so it doesn't, it doesn't seem to be there doesn't seem to be an interior optimum. So the only optimum then could be, so ln s plus 1 minus ln s is always positive, right? So it's, so that means this expression is increasing in s. So the minimum in MF should be attained at s equals 1. And at s equals 1, let's evaluate it. It will be minus 1/2 plus 2 ln 2 minus, 1 ln 1 is just going to be 0, so it's going to be equal to 2 ln 2 minus 1/2. So I think this is the final answer. I admit I'm not terribly confident in this because there's a lot of computation that goes into this answer, and it's easily possible that I got something wrong at some point. So I'll just go back and check my work here. So x plus 1 squared 2 squared is so this part seems fine. Let's go back here. So this is all fine. We end up with this. We add those up. We get one copy of xl and xy, that which cancels, and the other copy with some of these, it's 2xy fxy equals xy ln xy plus xy. That seems to check out. And then we write that like this because we're dealing with xy greater than 1, so we can divide by xy. And then we just integrate it with respect to y first. Y ln xy, y ln y. Yeah. Y ln minus y, and this is plus y, so those cancel. And then we integrate with respect to x. We get x ln x minus x, xy ln y. And then we get something symmetric, which is a good sanity check. Yeah. And for these independent things without correlation, this always sums to 0. So I think the answer we get is correct. Okay. And now, I'm not going to leave you hanging, so I'm not totally sure here that it's correct, so I'll actually check if it's correct or not. Yes, okay. So the answer is correct. This answer, I checked the solution, and this is indeed correct. So this is the solution of the problem. Well, since the solution is over, I'll stop recording now, and thanks for watching.